Hello and welcome to our 12th session. In this session we'll be doing some solved problems from chapter 6. These problems could be homework problems or exam problems. They are basically at the undergraduate level. One or two of them from chapter 6, which we won't be doing, are I think more in the graduate level. And to get started we'll be listening to a really wonderful, exciting performance of Gershwin's Rhapsody in Blue. Okay, this is kind of a broad outline for session 12. I've picked out 5 problems. They represent a cross-section of the kind of problems that one would encounter probably in an undergraduate course. I don't think any of these would quite get to the level of graduate, but certainly they're good, solid undergraduate level problems. So let's take a look at the first one, 6.2. Okay, this could be considered a trick problem, and the reason I say that or write that is because it's multiple choice, and I'm not a big fan of multiple choice problems. Generally, you can always eliminate, if there are 5 choices, as there are in this particular case, you can eliminate 2, probably 3, but you're always going to be left with 2, which are really hard to eliminate, and that's why it's tricky. So it depends on tiny little differences, but let's see if we can dope this crazy thing out. The statement asks the problem asks which statement best represents reality. Reality in this case is the reality that we have here in the problem statement. We have a material of p-type, let's say p-type silicon, and it's doped with holes, obviously, that's why it's p-type, of density Na. So in other words, we ion implant boron into the silicon lattice at a density of Na, 10 to the 15th, 10 to the 16th, whatever it is. We assume that if the doping is not too high, in other words, the Fermi level is not too close to the valence band edge, then all of the dopant atoms are ionized. So if you put in 10 to the 16th, you got 10 to the 16th doped ions. Which statement best represents reality? Okay. P is much smaller than N sub A, since not all the atoms are ionized. Well, that's obviously wrong, because we assume that all the atoms are ionized. That's basically what this equation states. And it doesn't state it explicitly. It states it in the form of the equation, but I think it's reasonable to assume that that's what they're saying. And of course, this is the exact opposite of statement A. The approximation P, number of holes, is equal to Na neglects thermal generation. Oh, that looks promising. So a more accurate expression is the number of holes is equal to the number of implanted atoms plus the thermal generation. Well, that's a possibility. We have to figure out if this equation is true, and you might suspect that it is not, and indeed that is the case. The most accurate expression is the number of holes is equal to the number of implanted atoms plus n sub I squared over nd. This is a statement of the law of mass action, and that looks really, really promising. Okay, let's see if we can find anything that's even better than that. This is probably better than this one, because this does not represent the law of mass action. Any expression for free carrier concentration that does not include the Fermi level is an approximation. I have no idea what that means. Since it's nonsense, we can eliminate. That's an easy one to eliminate. The whole concentration is simply equal to Na, since all dopant atoms are ionized. Well, it's true that all dopant atoms are ionized, but the whole concentration is not equal to Na. There is also thermal generation. So it looks to me like the correct answer would be C. Okay, good. And it says we should not be fooled by answer B, since the intrinsic concentration has been dramatically reduced by the presence of acceptor atoms. That's just another statement of, what is that a statement of? Remember that? That's the Chatelier's principle. Okay. Okay, let's go on to problem 6.6. A little bit more involved. We're going to do some mathematics here, and we're going to see where the mathematics leads us to. So consider a silicon sample, N-type, donor density, again donors, N-type, 10 to the 16th. So far, we're given not very much information, so it would seem to be relatively straightforward. However, we're going to look at temperature. We're going to look at the position of the Fermi level at room temperature, 300 Kelvin, and a much lower temperature, 100 Kelvin. 100 Kelvin is about 30 degrees or 25 degrees above the temperature of liquid nitrogen. So we're getting close to the temperature of liquid nitrogen. So this is going to be semiconductors in essentially liquid nitrogen conditions. The second one, and this is going to be, it looks difficult, it really isn't all that bad. The temperature for which the intrinsic concentration exceeds the dopant concentration by 1 order of magnitude, and the dopant concentration here, and I probably should have written that out explicitly, the dopant concentration at room temperature. So that's something to keep in mind. So the problem is not stated quite as explicitly as it should be. And they want the minority concentrations at room temperature, and I'm going to add here the minority concentration also at 100 degrees or 100 Kelvin. So let's get started with the first part, which is probably the most involved, although it doesn't look terribly involved. Let's see how it goes. So we start at room temperature. Well, we've done this before. I've included here the donor state ED. Generally, we do not include that in the energy band diagram, but we're going to be using that. It's about 50 millieV below the conduction band edge. And the Fermi level for this particular problem is 0.36 eV at room temperature above intrinsic. Now remember, I'm just going to go through this very briefly. We did 10 to the 15th in some detail. We found that for 10 to the 15th, the Fermi level is 0.3 electron volts above intrinsic, and for every order of magnitude, we increase the Fermi level, I should say the Fermi level rises if it's n-doped by 60 millivolts. So for 10 to the 15th, it's 0.3, 10 to the 16th, it's 0.36, 10 to the 17th, it's 0.42. Well, you get the picture. 10 to the 18th, it's 0.48. It's right over here. It's very, very close to ED. Okay. We've referenced the Fermi level to intrinsic. So to calculate the position, we wanted to do that explicitly. We would simply use the number of electrons in the conduction band is equal to intrinsic, reference to intrinsic. We know n sub I is equal to 10 to the 10th. KT is 0.026 at room temperature. We find EF minus EI is equal to 0.36 at room temperature. Now, if we lower the temperature to 100 Kelvin, which is, like I said, about 25 Kelvin above liquid nitrogen temperature, we expect the Fermi level to move up. As temperature goes up, the Fermi level moves down. As temperature goes down, the Fermi level moves up. Now, of course, at p-type, if the Fermi level was below intrinsic, as temperature goes up, the Fermi level would go up, and as temperature, did I say that? Yes, yeah. As temperature goes down, the Fermi level would go down. But in our case, we're n-doped, so as temperature rises, the Fermi level is going to move up. How far up? That's the question. Okay, so I think we'll be surprised by the answer. So sit down, hang on to your seats, and let's do it. Okay, so here's an explicit expression for the intrinsic concentration as a function of band gap and KT. And what we do here, this part of it is not terribly important because it's only to the 3/2. No big deal, but I pull out the 3/2 anyway, and then I do all of this stuff by itself. It's 3.9 times 10 to the 16th multiplied by the temperature raised to the 3/2. Okay, so Well, let's see what's going on. Instead of 300, this is 100. KT, instead of 0.026, 100 is 1/3 of 300. So this number here is 1/3, which means that the number here, instead of being 0.026, is 0.0086. That's 0.026 divided by 3. And if we put all that stuff in, which is not very difficult to do, just do that on your calculator, we get 3.4 times 10 to the minus 9th per cubic centimeter. Now let that sink in a little bit. At room temperature, if we put in the values for room temperature here, we get 10 to the plus 10. If we put in 100 degrees, I should say 100 Kelvin, not 100 degrees Kelvin. If we put in 100 Kelvin rather than 300 Kelvin, we get 19 orders of magnitude less. Quite a dramatic reduction indeed. And that's because that exponential tail, remember the Maxwell-Boltzmann distribution, that exponential tail depends very, very heavily on temperature. So if we lower the temperature, that tail just almost goes away. And that's what we're seeing here. It's rather interesting just to point out here that we can do the same thing. Of course, the whole business is right in here. This is what's causing this huge decrease in the intrinsic concentration. I could do the same thing by keeping room temperature, KT 0.026, but just increasing EG by a factor of 3. So from 1.1, I go to 3.3. I get the same number, pretty much. This is not a big deal. It's only a factor of 3 or 4. So very wideband semiconductors, for example, silicon carbide, which is a material which is very close to my heart, would also have this kind of intrinsic value. And just as a preview, that's the reason we can't make bipolar junction transistors out of silicon carbide, because you can't get a diffusion current because there's nothing to diffuse. There are no minority carriers per se at all. They don't exist. Okay. So now we put all that stuff into our expression. Same thing we had up here. Again, we're solving for E sub f minus E sub I, and it's relatively simple. We just put in, we're going to assume it's 10 to the 16th, and I'm going to point out something here because that may not be a great assumption. It works out, it's okay for this particular case. N sub I is this almost unbelievably small number. Take the logarithm of both sides, and 0.0086, that's KT, times the logarithm of 10 to the 16th divided by this very small number. That's what we're looking for, and we get 0.49 approximately electron volts. 0.49 electron volts above intrinsic. So look at what's happened here. This is intrinsic. We jumped from 0.36 right up to 0.49, which is essentially just about 20 millivolts under E sub D, which means that the assumption that all the atoms that we put into the silicon lattice are ionized, not so great. If it was precisely at E sub D, then it would be 1/2, because E sub f minus E sub I, or I should say, we'd have to look out the probability, but if you work out the probability, you'd find that if the Fermi level is at E sub D, the probability of ionization is 1/2. So this is not quite 10 to the 16th. It's probably about 6 or 7 times 10 to the 15th. But you know what? It's close enough for government work, as they say, so it's reasonably good. It's still okay. So here I said, okay, suppose it was, the Fermi level was at ED. It would be 5 times 10 to the 15th, because only 1/2 of the atoms would be ionized, and I would get guess what? 0.49 eV, same thing. Even though this has been reduced by a factor of 2, why do I get the same thing? Because I'm taking the logarithm. Now, it's not precisely the same, but rounded off, it's essentially the same. Okay, now we can perform the same calculation reference to the conduction band edge. Now, reference to the conduction band edge, we have the number of electrons in the conduction band is equal to this density of states at the conduction band edge, and reference to the conduction band edge, N sub C, E sub C. E sub F is below E sub C. Again, I'm repeating this, but hopefully it'll sink in, at least to me, if I keep repeating it enough. So this is a negative number. E sub C is bigger than E sub F. That's exactly what we want, because N sub C is big. N sub C is about 10 to the 19th. Is about 2.8 times 10 to the 19th. That's what it is, but it doesn't matter. Okay, so we calculate here with actually 2 times 10 to the 20th. Again, close enough. So at room temperature, this number is huge. At 100 degrees Kelvin, not too much less. And that makes sense because the T to the 3/2 doesn't really change things too much. It's going to be less because the temperature is less. However, it's not that big a deal. So we put all that stuff in, doing exactly the same thing as we did previously, and we find that it's minus 0.07. Why is it minus? Because this number is less than 1. We take the logarithm of a number less than 1. We get a negative number, 0.07 minus EV. So it's 0.07 or 70 millivolts below the conduction band edge. And if it's 70 millivolts below the conduction band edge, guess what? It's 0.49 above intrinsic, because 1/2 of EG is 0.56. So we get exactly the same answer, and that's quite nice. So it's interesting to continue this. We're not going to do that because this really gets into some strange stuff here. But if we go to 50 Kelvin, which is actually just a little bit less than liquid nitrogen, we would find that the Fermi level has moved up well into the conduction band, and there is essentially no ionization of the implanted P atoms. That should be N atoms. Strike that. Okay. In fact, let me do that right now. N. You stupid. Okay. We conclude that the thermal component to ionization. We conclude that there is a thermal component to ionization, and without this component, the atoms will be frozen out. So the ionization depends on the number of atoms which are implanted, the position of the Fermi level, but there's a little bit of a thermal component also. And if you get too cold, the thermal ionization essentially goes to 0, and it means, or it takes over and essentially freezes out the possibility of ionization. Okay, so here we are asked to find the temperature, part B, at which the intrinsic density exceeds the ionized donor concentration by a factor of 10. I would claim the problem is not very well stated, but we can assume that the doping concentration remains at 10 to the 16th, and we're at room temperature, and I probably should have put that in also. So we're looking for an N sub I of 10 to the 17th. That was B when the intrinsic concentration exceeds the doping concentration by a factor of 10. So once we realize that that's what we're looking for, it's just a matter of doing the calculation. So are we looking at a higher temperature, and are we looking at a lower temperature? Well, when we went to 100 Kelvin, we found that 10 to the 10th goes to 10 to the minus 9th. So it's pretty well obvious that we're looking at a higher temperature, and the question is, how high? Is it 1,000 degrees C, which would be about 1,300 Kelvin, or maybe a little bit less? So we're looking for a higher temperature. We write the same expression that we had previously, and we just try to see some values and we see what's going on. We put in, for example, 300 Kelvin and we do the calculation. We put in 400 Kelvin and we do the calculation. We find that the temperature is about 700 Kelvin, or about 400 degrees Celsius. Now we can attain this on a hot plate. It's pretty hot, but it's not that hot. So going only up to 400 degrees centigrade gives us an intrinsic concentration of 10 to the 17th. That's really quite remarkable. I should just say again parenthetically here that if we go to furnace temperatures, and we'll be looking at thermal oxidation, those are done at about 1050 Celsius. Very, very high. And there we're looking at degenerately doped intrinsic concentrations of 10 to the 19th, 10 to the 20th. So temperature matters. And that's the conclusion of this problem. Part C is quite straightforward. Part C says what is the minority carrier concentration at room temperature. Let's do it at room temperature. We know that the number of electrons, 10 to the 16th, that's the number that are implanted into the lattice. So we're looking for P. N sub I is 10 to the 10th at room temperature, so N sub I squared is 10 to the 20th, and we find P is equal to 10 to the 4th. And this holds at room temperature. However, what do we find at 100 Kelvin? Wow! Notice what happened to N sub I. It's now 3 times 10 to the minus 9th, and we square that, we get minus 18th, and then we take 16 bar off, we're talking about 0. And that's why we can never have anything that has to do with minority carriers. Minority carrier diffusion equation simply is not applicable at 100 Kelvin or for very wide band semiconductors like silicon carbide. Okay, let's move on to problem 6.7. These are more basic concepts in the sense that, well, we're not dealing with 50 Kelvin or something really esoteric. We'll just be using the Fermi-Dirac function and doing some relatively straightforward calculations and drawing some hopefully interesting conclusions. Maybe not so interesting, but we'll see. The math is not very difficult, but the physics can be a little bit tricky. So Part A says, under equilibrium conditions and above absolute zero, what is the probability of an electron state being occupied if that state is located at the Fermi level? And this is not really stated all that well. I should have said that the Fermi level is located at the electron state, because the Fermi level is the thing that moves. The electron state is stationary. But at any rate, this is what we call in engineering a softball question. And that's very important to recognize. There are some questions that are relatively basic. They don't involve a lot of thought. This is just a definition, so we'll see that we can answer this question in literally just a few seconds. Part B. The Fermi level is now positioned at the conduction band edge, and we want to determine, this is a simple, relatively straightforward calculation, the probability of finding electron or electrons at state E sub c plus kT. We want to know how many electrons are there if the Fermi level is positioned at the conduction band edge. How many electrons are there in the point conduction band edge plus kT? And since most of the electrons we know are within kT, we expect this number to be reasonably high. I mean, not not maybe 80 or 90%, but we would be surprised if it's 10 to the minus 10th or something like that. So it should be a reasonable number. Part C, the probability, and this is given to us, the probability the state is filled at the conduction band edge plus KT is equal to the probability of a state is empty at the same point, conduction band edge plus KT. Where is the Fermi level located under those conditions? This is the condition, and under those conditions, we want to find the Fermi level, position of the Fermi level. What is the probability of a state being occupied? Well, again, it's not stated perhaps quite as well as I should have stated it, but since we're dealing with conduction band, we would assume the probability of a state being occupied. This is for a donor. Now we can make it general. The probability of a state being occupied is given by the Fermi function, period. If it's a donor state, the probability of a donor state being occupied means that that donor has not given up its electron. It has not been ionized. What is the meaning of a donor state being empty? In this case, we specifically state donor state. If the donor state is empty, it means it has given up its electron and it is ionized. And that is 1 minus the Fermi function. What does it mean if an acceptor state is empty? If acceptor state is empty, it is not accepted an electron. It has not accepted an electron, therefore it has not contributed a hole to the valence band. It is neutral. Okay, so we won't actually answer those questions when we do the calculation because we just did. Okay, and repeat part C for a state with arbitrary level energy E located anywhere within the energy band diagram. Okay, so part A, relatively straightforward. The probability of an electron state being occupied is given by the Fermi function. And if the Fermi function is equal to E, then E sub f minus E sub f is 0, and 1 plus anything to the 0 is 1, 1 plus 1 is 2, so the probability is 1/2. The probability of electron occupancy at the Fermi level is by definition 1/2. And we've seen that a number of times. Now for part B, we place the Fermi level at the conduction band edge. So we say the Fermi level is equal to E sub c, and we ask what is the probability of finding an electron KT above the energy band, the E sub c, the electron energy band, conduction energy band edge. Okay, now we have already determined that the majority of electrons are within KT. That's a restatement of what we mentioned just a minute or so ago. So we will expect this probability to be reasonable. So we write the Fermi function for EC plus KT, that's here, minus E sub f, but E sub f is equal to E sub c. That's what the problem states. So E sub c minus E sub c, KT over KT is 1, and that probability is a little over 25%. So all that makes sense, and it's just a matter of using definitions and using some basic logic. Here in part C, we're asked to find the probabilities, and since the Fermi function is a probability, we'll be equating Fermi functions under somewhat different conditions in this part. The Fermi function gives the probability of electron occupancy. 1 minus the Fermi function gives the probability that the state is empty. So this is the probability the state is occupied. This is the probability that the state is empty. Let's go back to part C here. So they say the probability is occupied, filled, occupies the same thing, is equal to the probability that it is empty. So we have those two probabilities, and we simply equate them. And here we go. Probability occupied is equal to the probability it's empty. Put in the numbers, and we solve. Okay? Here again, we've done this, I believe, at least one more other time. We have to just combine these two terms, which we do here. And we find ones go out, the denominators are equal, therefore the numerators must be equal. Here's the numerator on the right side, here's the numerator on the left side. We take the logarithm of each side. The logarithm on the left side brings down EC minus plus KT minus EF, and logarithm of 1 is 0. So we find that the Fermi level is equal to EC plus KT. Now, you might want to just read this. We could have obtained this by inspection. Think about it and see if you can agree or agree with the logic. And if you don't, ask me a question and I'll explain it in somewhat more detail. For an arbitrary level E, we do exactly the same thing, and we proceed in exactly the same manner, and we find exactly the same result. This is a result that could have been, again, expected almost by inspection. So that's problem 6 point, what was that, 6.7, I believe. Now we skip over to problem 6.9. In 6.9, we explore the concept of deep dopants. We looked at deep dopants for compensated doping, and here we're going to do it a little bit more, shall I say, the problem in silicon. Remember that compensated doping doesn't work for silicon. However, we're in the theory range right now, so we can do whatever we want, and we can assume that all the numbers are precise. So consider a silicon dope sample with doping level located 0.3 eV below EC. Now that is not shallow, that is deep. What is shallow? 50 milli eV. This is 300 milli eV. So this is called a deep donor, or sometimes called a trap. Okay. The doping concentration is 10 to the 16th. In other words, there are 10 to the 16th of these bad boys located 0.3 eV below EC. The Fermi level is given. We're given the Fermi level, and it is 0.2 eV below the conduction band. So let's take a look at that and on the energy band diagram. Here is the electronic state. It's supposed to be up here. All the other times we've seen it way up here. Now it's really far below. The Fermi level is above the electron state. That means that the probability that we have donation in this region is extremely low. When the Fermi level is above ED, the probability of ionization is low. We've seen that a fair number of times. So we want to calculate the required doping concentration of shallow acceptors in order to compensate the deep donor traps and make the sample intrinsic. Again, I would repeat, in this particular case, everything is precise. In practice, probably wouldn't work, but in theory, a lot of things work that don't work in practice. So this is a calculation in theory. Okay. So we use the equation that the number of ionized donors, which is equal to the number of electrons in the conduction band, is equal to the doping dose, in this case 10 to the 16th, multiplied by 1 minus the Fermi function. The Fermi function gives the probability of occupancy. We want the probability of non-occupancy, of donation, and we expect that will be relatively low. Okay, so here we go. Just repeat it, and I put in 1 minus the Fermi function of E sub f. Now, if it was the Fermi function of E sub f, I would have ED minus EF. Since it's 1 minus the Fermi function, we do that trick where we add these two fractions, and what happens is that the argument in the the Fermi function flips. Instead of ED minus EF, it's EF minus ED. Now we know EF minus ED. Where is it? This is EF, this is ED, this is definitely not drawn to scale. So this distance here from EF to ED is 0.08 EV, or 80 millivolts. So we can just put that in, and right here, divided, because it's room temperature, so it's 0.026, number we know and love, and we find that ED plus is equal to ND plus, the number of ionized donors equal to the number of electrons is equal to the dose times 0.044. And again, that's a very small number. 4% are ionized, and the other 96% are not ionized. And that's because the E sub F is above E sub D. Well, from this point on, it's pretty straightforward. The dose of deep donors is 10 to the 16th, and therefore the ionized donor concentration is the dose ND multiplied by the probability, or 4.4 times 10 to the 14th. To compensate for that, we just use the exact number. It's got to be exact. It can't be 4.2, 4.3 even times 10 to the 14th. It has to be 4.4 times 10 to the 14th of shallow acceptors, and presuming that the shallow acceptors would all be ionized, and they would exactly compensate for the ionized donors. Okay, so that's it. And I don't know why I repeated this. Let us take that out. That was rather silly. Not this great problem. I don't think we should do it twice, that's all. Okay, so we're going to end with the last part of the finale to Rachmaninoff's Piano Concerto No. 2. It's a wonderful, wonderful performance. So enjoy, and we'll see you next time.